Good. And I think we are set. So we'll continue with the support vector machines. I hope you can see the screen.
Yes, sir.
Yes?
Yes, we can see this.
Okay, that's good. So support vector machine is essentially a maximal margin hyperplane classifier. And we have seen the support vector machine in the context of points where the points are belong to the original space. Basically, we have seen the linear case of support vector machines. Linear in the sense we don't do any transformation of the original data points. We learn the support vector machines in the original data space. And in that, we have seen two cases. One is a hard margin SVM and a soft margin SVM. Hard margin SVM is the case where the points belong to two classes. Neither of the points belong to the two classes cross the boundary, which is called the hard margin SVM. And the soft margin SVM is the context where we allow certain noise, where we some of the points can fall off the boundary and make some errors, and then we penalize those points. So the problem of learning support vector machines, primarily like the classifier, was posed as an optimization problem with primal variables represented as W and V, which are essentially parameters of a hyperplane. And we pose the problem as an optimization problem in the primal variables W and V. And then we have seen that this can be better represented in a Wolfe-dual form for computational convenience, and then can be solved further. So the primal variables in the SVM problem are W vectors, or W and V values, and then the dual variables, corresponding dual variables, where the Lagrangian multiplier is alpha values, where the number of primal variables will be equal to the dimensionality of the data point. That's what I said a little while ago, and the number of dual variables will be equal to the number of points involved in the training set. Right, that's where we stopped, and we have seen how to write the Wolfe dual. How does derivation happens, and what's behind it? What is the mathematical fundamentals behind it? Today we are going to see nonlinear support vector machines. Right, learning a support vector machine in the original data space is perfectly fine. So what an SVM does is SVM can find the best hyperplane, that is a maximal margin hyperplane, if there is a separability. Right? What is a maximal margin hyperplane? It's a hyperplane which is midway between the canonical hyperplanes, which marks the boundaries of the two classes. So we have got points belong to two classes. You can mark the boundaries of those classes by what is called the canonical hyperplane at W transpose X plus B is equal to 1 and W transpose X plus B is equal to -1. That's the way you actually rotate W and change B in such a way that for all the candidate hyperplanes you get corresponding canonical hyperplanes, and among all the candidate hyperplanes, which is W transpose X plus B equal to 0, you find that hyperplane where 2 by norm W, which is a margin between the canonical hyperplanes, is maximized. So maximize 2 by norm W with respect to the conditions of correct classification, which is nothing but yi into W transpose X plus B is greater than or equal to 1. Right? We don't allow anybody in the boundary also. So that's what we have seen, and we allowed points to fall off the boundary. There we came up with the notion of a soft margin support machine, where you had rather than minimizing or maximizing 2 by norm W, you essentially minimize norm W, because you can't do anything with 2. So minimize norm W, which in a convenient form represents as half of W transpose W plus C into C zeta I, where zeta I is the penalization corresponding to the points which are falling off the boundary. And then we allowed the little allowance for those points as yi into W transpose X plus B is greater than or equal to 1 minus zeta I, and you get the corresponding primal representation of the soft margin SVM. You have taken you have represented that in a Wolfe dual form also, and then we have derived and upload the content for it. You have derived the Wolfe dual equivalent, and then you get the problem represented in terms of the Lagrangian multipliers, and those you solve the problem for the Lagrangian multipliers, and that's where we stop. So this is all fine as long as there is separability in the original space. This is fine. So there is an interesting theorem called Cover's theorem, and the statement of the theorem is it says that separability patterns of data vectors in a high-dimensional feature space are more likely to be separated than vectors in low-dimensional space, which says that if you have points belonging to say an n-dimensional space, if you can transfer that to maybe a very high-dimensional space, then the chance that you may get a separability, you may get a linear separability is more, right? And following this principle, Vladimir Vapnik and the statistical learning theory experts or researchers explored this domain and said, hey, if we can prove, we have the problem in the original space, which is represented in terms of the training vectors in this space, which is xi, yi pairs. And if we can pose this problem in that high dimension space where there is potential separability through a function, say phi, they call it phi. If there is a transformation of the data points belong to this space, right, from the original space, the data space, to a very high dimensional space through a transformation phi, which you see in front of you, phi, then what we can do is we can represent those points which are essentially like transformed representation of xi's. If they represent that as zi, all that happens is like instead of xi yi pairs, in that space you'll have zi yi pairs, where zi is nothing but phi of xi. If we can do an explicit transformation, I don't know what that space is, and I don't know what the transformation is, right? And that'll be a high dimensional feature space where you will have an equivalent representation for xi, which is zi, which is phi of xi, and that such spaces are typically in the case of SVM, such spaces are reproducing kernel Hilbert spaces. I don't want to get into the topology context. So the essential requirement know-how we need to have here is, if we can pose a problem in a high dimensional feature space called H, your problem may become linearly separable, right? Owing to that, following that principle, we said, yes, let us then write what we call on the similar lines that are soft margin SVM, can we represent an SVM and then solve the problem in the HS space. Rather than solving a problem in the X space, can we solve the problem in the transform space, which is where the vectors are zi's and the corresponding labels doesn't change, which is yi, right? Can we solve the problem in the transform space, which is called the high dimensional feature space, the Hilbert space. All right, that's what people attempt. They represented the problem. This problem is very similar to the soft margin SVM case in the linear context. So minimize WB and zeta, right? And minimize the function is like with respect to these variables, half of norm W square plus C into Z zeta I, where the data vectors are not xi's anymore. These are transform vectors in the high dimensional space. These are zi, so yi into W transpose zi plus d is greater than or equal to 1 minus zeta I. That's the only difference. Where we know that zi's are essentially phi of xi's. All right. And the corresponding Wolfedial on the same line. This is an exercise that I have asked you to do, right? Find the Wolfedial equivalent for it. How do you do it? You write the Lagrangian and you write the maximization problem in the dual form, and then Lagrangian dual essentially, right? And I've shown you, right? I've written it for you in a paper and gave you that. If you studied it, you'll be able to realize this. So you write the corresponding Wolfedial also. The Wolfedial is on the same lines as that of the hard margin case. The only thing is, instead of xi xj here, you get zi zj, because currently the vectors are in a high dimensional space, not in the x space. It is in a z space where z is xi, is phi of xi. Right? That's the only difference. You get very same Wolfedian in terms of the z variables. And see here, the only computation involving, I've already told you in the last class, the only computation involving z's in this space, in this computation, in this dual problem, which is a Wolfedial problem, is a dot product between the vectors zi and zj. Then the question that arises at that point in time is, all I need, right? See, I've got xi yi pairs, and to do computation of this particular what we call context, in order to learn SVM in this context, it doesn't look feasible because the data vectors are not linearly separable. But Cover's theorem says that if I pose this problem in a high dimensional space, there it may become linearly separable. Is there a space where I can do this? If there is a space, let's call that transformation as phi. And I've got vectors there, and I don't know whether I will do an explicit transformation or otherwise. So I've got vectors, I represent those vectors as zi's. And in that space, all I need to, in order to do a SVM learning in that space, all I need to do is I need to compute the dot product of the transform vectors. That's the only computation I need. If I can compute this somehow, right, in that, basically, if I can compute the dot product of the vectors, of the transform vectors in that space, I'm done. I don't have to go any further. And it turns out that there is a class of functions which are, let's call it magical functions, which when given xi and xj as inputs, it can compute you zi and zj, and such class of functions are called kernel functions. Right? It turns out that there are certain class of functions. If you put xi, if you input xi and xj, which are the original data vectors in these vectors, what it does, it'll return you zi.zj is essentially phi of xi dot phi of xj. Right? And in mathematics, such functions do exist, and such functions are called kernel functions. So the moment you say that there are magic functions of this kind, there are functions which can take input in the original space and compute the dot product of the transform vectors in the transform space, which are called kernel functions. You can essentially implement the SVM learning, or you can do SVM learning in the other space. Instead of, if you look at it, you have to compute this. Now with the introduction of kernel functions, what happens is like zi dot zj can be replaced by k of xi dot xj. Right? These are functions with two, which takes two vectors, the original data vectors as input, and return you the dot product of the transform vectors, which are essentially zi dot zj, which is what I need. Right? And it turns out that such functions do exist. Right? Good. Let's move on. All right. So then you essentially, like, once you have that, you can go at the KKT conditions, which are very similar to the soft margin case, which will say like, okay, points which are basically like non-zero C values. So there are two cases. Points, the Lagrangian multipliers alpha is will have three cases primarily. The three cases are the alpha I can be like C, alpha I can be 0, and alpha I can sit between 0 and C. And you can see that very similar context will exist as that of the soft margin SVM, and there is no difference. The only difference is in the Wolferial form, instead of zi.zj, we'll have k of xi dot xt. And in double transpose, so in the transform space, you don't anymore work with x vectors, you work with z vectors. So w dot z, essentially w transpose z plus b, will be equal to alpha I by I. Instead of that xi dot xt, you'll have zi dot zj, which are essentially which can get replaced by k of xi dot xj plus b. That's the only difference, right? Instead of xi dot xt, you'll have k of xi dot xt. That's the only difference when it comes to computation. All right. So by a suitable selection of these magical functions called kernel functions, instead of doing your SVM computation in this space, you can do SVM computation in the transform space called the high dimensional feature space, which is typically represented as H, without having to explicitly compute. All you do is you plug in that kernel function, so that you don't have to do one by one transformation of every point from this space to that. Rather, you have certain function, you give pairs of data points over here as input to this function, and that function will give you the dot product of the transform vectors in that space. And this particular technique is called kernel trick. And SVM is the one that introduced this kernel trick. And kernel trick is not limited to SVM. And class of algorithms which essentially uses this principle, where in order to do algorithmic learning in a transform space, rather than doing an explicit transformation of all the vectors from the original space to the data to the high dimensional space where that algorithm is actually learning, you can leverage the principle of kernels, which essentially will do dot product computation in that space, and then what you do is you just input the points in the original space to this kernel function. It will provide you the dot products of the transform vectors in that space. So any algorithm which can leverage this principle, where any algorithm which requires only dot product computations in the transform space, can essentially implement such techniques without doing explicit transformation. That particular technique is called kernel trick. By choosing a suitable kernel function, any machine learning algorithm, that's the last statement, by choosing a suitable kernel function, any machine learning algorithm that requires only the inner product between data vectors in the transform space can be kernelized, can be turned into a kernel method, and this technique is known as kernel trick. And SVM introduces this technique. You can see kernel k-means, kernel bursts, kernel PCA, etc., etc. There are n class of algorithms out there in the kernel class of algorithms. Then the natural question that you will ask is like, what can be a kernel? This is a very simple example of a kernel, right? see, we have points belonging to, say, let's call it K. We have points belonging to two-dimensional space, right? Let's suppose that original space is T is equal to 2, and the transform space is a three-dimensional space. Just for, this is a toy example. It's a toy example. It's not at all realistic. So we can choose a mapping. Let's choose the mapping as AB. Basically, like it's basically this is the transformation. Given A and B as the input, this is the transform vector. If you give a vector with what you call, this is your original data point AB, the data vector AB, if it is given to the phi transformation, let's see the transformation, explicit represent transformation. The transformation from the original, this is a two-dimensional vector, and that get transformed explicitly into A square root 2 AB and B square. This is the representation in the transform space. If in that case our original space is two-dimensional, the dimensionality of the original space is two-dimensional, and the dimensionality of the transform space is three-dimensional, R3, right? From R2 to R3 is the transformation, right? Let's U1, U2, let's our vectors, as in our xi, xj, let the vectors be, input vectors be U, this U represented by U1, U2, and V represented by V1, V2. So what we need to compute is the dot product of the transform vectors. Phi U, these are essentially the Z vectors. Is Zi dot Zj is essentially phi of U dot phi of V. What is phi of U dot U phi of V? It's basically you represent, right? You get so the U will be represented as U1 square root 2 U1 U2 and U2 square. That will be the representation of phi of U, and phi of V will be V1 square root V1 V2 root 2 V1 V2 and V2 square. And if you take the dot product, you'll get it's essentially like those vectors, right? U1 square, V1 square, 2 V1 V2, U1 U2, V2 square, V2 square, which is essentially UV the whole square, right? U dot V the whole square. U dot V is, what is U dot V? It will be U1 into V1, right? U1 into V1 plus U2 into V2, right? Then if you actually like kind of take the whole square of that, what you get is U1 U2 the whole square plus U1 essentially like U2 V2 the whole square plus 2 into U1 U2 V1 V2. That's essentially the thing. So this is nothing but U1 UV the whole square. Let's represent that as K U comma V. Then what happens is, like, when you give U and V, you can just compute UV the whole square without doing this explicit, without computing this. You get the dot product. So the dot product of what you call dot product of phi of U and phi of V will be UV the whole square, which is the function, right? You get the corresponding dot product computation in the transform space. That's how it's a simple illustration, and this is an example for a type of kernels called polynomial kernels. All right. Then the question that this is slightly mathematical, comes from a little deep math. What says is, any function which takes two vector inputs, and gives a real number as the outcome, can it qualify to be called a kernel? All right. Can any function become a kernel? And the answer is no. The kernel has to have a positive semi-definiteness. That's what is displayed over here. And the theorem that qualifies any function as a kernel, all right, that given a function from RD across RD to R, which is essentially like takes two vectors in the d-dimensional space and returns a real number, and there exists a mapping phi, an expansion in the form of that kernel computed will be equivalent to the dot product of the transform vectors. If and only for every real value function of this type, which is bounded by infinity, we need to get this. And the meaning of this is you need to have positive semi-definiteness, right? That's the meaning. So the Mercer's theorem qualifies any functions to be qualifies any function that is a potential candidate for a kernel function. So any function which satisfies Mercer's theorem can be considered as a kernel function. And some of the kernels here are linear kernels. K xi dot xj is xi dot xj. If you plug in this kernel to the original, this particular SVM, k xi dot xj is nothing but xi dot xj. In this particular algorithm, k xi dot xj is nothing but xi dot xj, which means that this xi dot xj will become k xi dot xj will become xi dot xj, and essentially what you get is a linear hard margin or soft margin SVM, right? That's what it is. So one of the it's a trivial case. Basically, the linear it's a linear hard margin or soft margin SVM. It's a linear SVM. All right. Another kernel which is interesting is Gaussian kernel, which is the most practical kernel, where it's parameterized by Q, essentially representing what you call the width of the kernel. It's called. And you can see that this is the Euclidean distance between it takes the Euclidean distance between the data points under consideration and scale it by Q, and e raised to minus Q of that will become the kernel value. And you can see is this a similarity to similarity? This is similarity, right? A polynomial kernel, the one similar to that. So we have seen xi dot xj the whole square. 1 plus xi dot xj the whole recipe is another example for a kernel function. And these are not the only kernel functions. Any function which satisfies Mercer kernel can be called as a kernel, can be qualified as a kernel. So there are kernels which are defined between graphs. There are kernels which are defined between tree structures. There are kernels defined between sentences. There are kernels defined between complicated, arbitrary shaped structures in the dimension space. So these are trivial kernel functions, and most of the practical cases Gaussian kernel works. And Gaussian kernel, those who are interested to go further, Gaussian, these two have an infinite dimensional resolution. This turns out that if the kernel applied is Gaussian kernel, the actual transformation happening is to an infinite dimensional space, and there is evidence and enough explanation available on the internet. It's only for those who are interested in the further exploration of the thing. So all I want to say is, how do you solve a nonlinear case within a support estimations? The idea was, Cover's theorem says, like, let us pause this problem. Instead of solving it here, let's pause this problem in an infinite or a high dimension space where you can do the same thing or similar things as that of the linearly separable context. Then what is that high dimension space? All right, and let's call the transformation as phi. And if such a space exists, all right, such a space exists if there is a kernel existing. Right, that's what it is, and the qualification for that is Mercer's theorem. Mercer's theorem says, like, if you can find a function which satisfies Mercer's theorem, which can be qualified as a kernel, then there will be a space, and that space you'll be able to do dot product computation, and it'll be a dot product space or a net product space, and where your dot product is equivalent to the computation achieved by the kernel. That's what the Mercer's theorem essentially says. Right? If we can do that, we can do essentially, instead of doing explicit transformation of your nonlinear case to that space where there is linear separability, you essentially plug in the kernel to the SVM formulation and you solve the problem in that space without doing explicit transformation of every other point. And that's the basic idea behind nonlinear SVMs. All right, and that's where I was just explaining, and Mercer's theorem becomes the qualifier for it. And these are some of the examples of the kernel. And once you do that, how do you solve? You don't solve, right? SVM problem has been solved in many ways, right? These are some of the ways in which you can look at it. People have directly tried to solve the primal problem at times. People have tried to solve it with with matrix operations. People have tried to solve it with chunking, iterative chunking, solve KP problem in a small subset, rather than you're taking your original, the old training data. Let's take a small working set and solve the problem there, right? Try to find optimize in that context. The parameters can be optimized in the context. Gradient projection, which is a standard optimization technique, people have leveraged. Iterative chunking is a special decomposition method. General decomposition, essentially breaking down the problem into smaller cases and trying to solve it. But the most successful, right? These are all attempts by the optimization gang, and the most successful one. This is what I urge you to go back, look at this paper by Plant from Microsoft Research. This talks about sequential minimal optimization, SMO algorithm, where the problem size, like in the training set, at any point in time, you'll take 2 points and you try to solve the problem here with 2 points. And we don't go into the details of some algorithm. And there was some bug in the original algorithm, and my co-author and co-guide during my PhD, Mrs. Shirish Shavade and the gang, they solved that problem. So modified SMO is a standard support machine solution strategy, right? And people like us has worked on, see, my PhD is also on an SMO, on a SVM solution strategy, which is an approximate solution. We want to get in there. So essentially, you solve the Wolf radial. That is the most accepted method. And if you want to do multi-class classification, now we have considered only a 2-class context. If you want to do multi-class classification, There are multiple strategies people use. You can actually do a 1 against all. You have got 10 class contacts. I'll take class 1, and class 1 becomes my current concentration, and everything else is considered to the other class. So that is this class versus the other class. Class 2 versus the other classes. Class 3 versus the other classes. So it's called 1 against all. So you pose your entire classification problem as like 1 against all. Again, 1 against all classification. There are 10 classes, you'll have 10 1 against all classification problems. And the other one is, if there are 10 classes, 10C2. So you can take what you call 1 against 1. You can choose 2 at a time and try to classify. And among that, you do a voting. That's the strategy. All right? And that's one of the classic approaches to multi-class classification using 2-class classifiers. And direct multi-class classification in the case of SVM was also attempted. And one such attempt is called multi-class SVMs by Shaw, Taylor, and Weston. Then there is struct support definitions by Jackims and the gang. Jackims, you can look at it. They have implemented what is called not LibSVM, SVM Lite and struct SVMs of Cornell University. It's Professor Jackims of Cornell University. You can look at it. I'll give you the link for that. So there are multiple attempts to solve multi-class support mission problems. Also, I have also worked on a multi-class support mission algorithm called the multi-class core-vector mission. You can look at the paper in 2006 ICML and corresponding JML algorithms. All right, and implementation is abundant. You got a lot of implementations, and I want all of you to look at these 2 implementations. These are the classic ones, and every other implementation uses these. They have actually like kind of leveraging these implementations, which are primarily in C or C++. SVM Live by Joachims of Cornell University, and this is by CJ Lin. CJ Lin, I think he's somewhere in. It's Chang and Lin, and we are connected to like our research group is connected to both these guys, and all the new age packages either utilize the LibSVM or the SVM Live of Joachims, right? That's what it is, and then. There are many R implementation, MATLAB implementation, Hero SVMs, LibSVMs, and many other CVMs are out there. And those are interesting kernel machines. Support vector machines.org is a very good context. And I'll give you there are tutorials around bugs. Bugs tutorial is one of the most celebrated tutorials. There is a tutorial by Professor P.S. Shastri of IISc, and then there's the book on SVM by Nello, Christiani, and Shaw Taylor. So that's also an interesting book. I'll give you some tutorials out here, and that's pretty much for today on SVM. So all I want to say is